We're going to talk about limits and continuity of multivariable functions. And before we jump right in, let's go back to single variable calculus so we can review our ideas of limits and continuity in single variable. So we had, when we were talking about single variable, the limit as x approaches a of a function, well, equals a number. Now, if the limit exists, in other words, because I wrote this, it's the limit exists. Now, what does that mean in single variable calculus? Well, there's a. That means that as the function comes in from the left side or comes in from the right side, that the value, that the y value of the function is the same, L, on both sides. Now I drew an open circle there because it doesn't mean the point has to actually exist. For the limit to exist, it's just the number from this side has to equal the number from that side. What does it look like if the limit doesn't exist? Well, if the limit doesn't exist, we got to draw pictures that look like that, right? Limit from the left doesn't look limit from the right. You check both paths and then you say the limit doesn't exist. Check the limit as x approaches a from the negative. Check the limit as x approaches a from the positive. So this would be limit doesn't exist. Now, as far as continuity goes, I drew it like this. The function is discontinuous here because I put a hole in it. The limit still exists. If I want the function to be continuous, then I have to fill that hole in. Or I guess I would just draw a continuous, well, I would just draw it as a continuous line. So in that case, the limit exists and is equal to a number, and I get the same value, L, if I just plug the a in to the function. So that means that that hole is filled in. So we talked about the limit exists if the limit from the left equals the limit from the right. We said the function is continuous if the limit from the left is equal to the limit from the right, or the limit exists, and is equal to the value of the function. So you could have the limit exist but not be continuous if I put a hole in it, or you could also get this situation. Sometimes the point is moved, so that's not continuous, but the limit does exist. Now, can you have, I'm still in single variable calculus here, can you have the function be continuous but the limit not existing? No, you can't. So if we say that a function is continuous, that means the limit exists. Because continuous means there's no break, so then the limit from the left has to equal the limit from the right. But just because the limit exists doesn't mean, like in this case, the limit exists but it's not continuous. So the arrow doesn't necessarily go backwards. But let's just talk about limits for now. When we're talking about limits, in single variable calculus, the limit existing meant that the limit from the left equals the limit from the right. In multivariable calculus, well, there's more than two paths. I mean, in single variable, we checked all paths, but there's only two, coming from this side and coming from that side. Check both. If they're the same, then the limit exists. In multivariable, there's an infinite number of paths. So let's go and look at what our multivariable is. And we see our analog here of our limit. It's not the variable, the independent variable x approaching a. The independent variable is a point, xy point is approaching the ab point. And the graph is continuous if the limit exists and it's equal to just plugging that AB point into the function. So you can see how it's an analogous situation to our single variable calculus. But computationally it's difficult because we're saying here for all paths. It was conceivable, it was possible in single variable to check all paths because there was only two. It's not conceivable, it's not, we can't mechanically check all paths in multivariable calculus because we don't even mean all straight line paths into the point AB. We mean all paths. So if now I'm in multidimensional calculus, so I'm just looking at there's the point AB, and there's some kind of surface over top of this. So I need to check all paths in. So all paths, but there doesn't even have to be all straight paths. Maybe some kind of crazy winding path that goes in like that. All paths have to give me the same limit value for the limit to exist. And it has to equal to, when you just plug the AB in, for the function to be continuous. So let's talk about the limit right now, because that's the thing that that we could actually ask questions on right now. How do we prove that the limit doesn't exist? Well, if it's infinity or plus or minus infinity, some people say that, okay, the limit doesn't exist. I would say a better way to answer that question, if you get infinity, is to say it's infinity. Then we can argue later whether infinity exists, but it's a better answer than just DNE does not exist. But if the limit exists, then I get a number less than infinity, say a finite number, for all paths. So less than infinity, but also greater than minus infinity. So not infinity. So if we can show that this is not true, in other words, if I want to show, let's look at this example. If I want to show that the limit doesn't exist for this function, the function x minus y over 2x plus y, to show the limit doesn't exist, all I have to do is find two paths that give me a different limit. Then it's not the same for all paths because I found two different, and then I'm done. The limit doesn't exist. So let's take a look at this function here. We're approaching the origin. Now I can't just plug 0, 0 in because that'll be 0 divided by 0. So it's not a continuous function as it's written. The f of x, y equal to this expression, not continuous. And there's also like a dividing by 0 problem here, right? The domain doesn't include any place where we're dividing by 0. So the domain is all values, all x, y points such that y doesn't equal minus x. So that y equals minus x line, that's taken out of the domain. If I were to sketch the domain, let's do that for now. If I were to sketch the domain here, those are supposed to be straight. That's a y. I'm putting a dotted line here for the line y is equal to minus 2x. So that's okay, just not on this line. When I get close to this line, well, I start to divide by 0, and so anywhere you get close to this line, the graph should shoot off to infinity or minus infinity, depending on the sign of this. So anytime I get close to this line, the graph should either go down to negative infinity or up to positive infinity. Except I'm curious about here, that place like that we're actually taking the limit. As x and y get closer and closer to 0, the denominator gets closer to 0, so then you want to say, oh, the limit goes to infinity, the function goes to infinity, except the top also gets closer and closer to 0. So maybe 0 divided by 0, that's one of those indeterminate forms. So maybe this goes to a number, maybe it goes to 0, maybe it goes to infinity, we don't know. We want to show that the limit doesn't exist, so we want to find like two paths into this that we get a different answer. So let's check the two paths. The first path I'm going to check the easiest path. Let's check down this axis. So I'm coming in on the y-axis. So the first path I'm going to check is if I'm coming in here, when x is equal to 0. I'm checking that path. The second path I'm going to check is when y is equal to 0. I'm coming in on this path. So let's just check those two paths. So on the path x equals 0, well, everywhere on that path, the limit, since x is already 0, that's just y approaching 0. And if x is already 0, that's 0, and that's 0. So it's this function, and yeah, it's 0 over 0, but if I do my canceling, that's minus 1. So everywhere along this path, the value is approaching minus 1. This limit is minus 1. What about the other path when y is equal to 0? Well, on the path y is equal to 0, we have our limit. Now, y is already 0, so it's just x getting closer and closer to 0. It never gets to 0, we're only approaching that value. So y is already 0, so this is gone, and this is gone. And, oh, that's equal to a half. So on one path, it's minus 1. On another path, it's a half. Since they're not equal, since the limit on this path is equal to minus 1, is not equal to the limit on the other path, then we say the limit doesn't exist. So show the limit doesn't exist, just find two paths where I get a different answer. We answered the question, but what does this look like then? Well, here it is. There's our x, our height is given here. Let's look straight down on it. So I'm looking straight down. Y goes like this, x goes like this. Here's my y equals minus 2x line that we're not allowed to be on. It wasn't in the domain. So I can see it removed here. As I get closer, the graph goes to minus infinity here or plus infinity there. There it's shooting off to positive infinity. Here it's shooting down to minus infinity. But it's 0, 0 that I'm thinking about. Now as I approach along x equals 0, I'm going along this line here, and it kind of looks like I'm hitting minus 1 here. As I approach on the y is equal to 0, yeah, it's higher. It looks like it's approaching a half. Let's zoom in, because this is going 3, 3, 3. Let's make this, so see if the picture helps us out at all. It might not. So I'm zooming in. I still see that y equals minus 2x that I'm not allowed to be on. But do I see, as I approach with x is equal to 0, I'm getting closer and closer to, it's harder for me to see it, right? Here's where y is equal to 0. Yeah, they sort of touch higher at a half. As I'm approaching in here, they touch lower at minus 1. Yeah, okay. I can see the limit doesn't exist there. We've proven that it doesn't exist. We've proven it algebraically, and the picture's kind of giving us an indication that what we did was correct. Let's do another example. Show the limit doesn't exist. So same plan. Just find two paths where I get a different answer. Okay. Last time, we took the limit on the two axes and got different answers. Oh, wait a minute. Show the limit doesn't exist. Can I even plug 0, 0 in there? No, it's 0 over 0. The domain problem, though, the denominator is 0 on this parabola where y is equal to minus x squared. So this function can approach infinity. But I'm worried about where when the point approaches 0. So let's do the same thing. Let's take our limit. Let's try the same idea. On x is equal to 0. On x is equal to 0, the path coming in, so I'm riding down the y-axis. So if x is already 0, I'm getting, that'll cancel out to be minus y. I'm getting 0. Okay? It doesn't tell me anything because I need another path. Let's try another path. So on y is equal to 0, on y is equal to 0, I'm riding in on the x-axis. So y is already 0. This disappears and this disappears. So now I'm getting a half. So the limit doesn't exist because I found two paths that are different. Let's see what this one looks like in the picture form now, and see if we can see that parabola. So x squared minus y squared on the top. And on the bottom, it's 2x squared plus y. Okay. Oh, I totally see, I think I see this upside down parabola that I'm not supposed to have. Let's zoom out for a second. Yeah, I see that upside down parabola that I'm not supposed to be on. As you get closer and closer to that upside down parabola, you start dividing by things closer and closer to 0, so it shoots off to plus or minus infinity. It shoots off to negative infinity when I'm outside the parabola. It looks like it shoots off to positive infinity when I'm inside the parabola. But we're thinking about what happens as we approach the origin. So as I approach along, so I've set y equal to 0. That looks like I'm getting that 0. If I approach along x equals 0, let's go in. If I'm approaching along x equals 0, I'm riding on this line here. And it looks like I'm riding on this line here. So as x is equal to 0, yeah, this is the line y equals minus, or the function equals minus y. I'm getting 0. As you ride along the y equals 0, it's going to a value of a half. Everything canceled out when I was approaching with y equals 0, so it was just this flat line there. Anyway, the paths aren't equal, the paths don't line up, the limit doesn't exist. Now, just because, what if these worked out to be the same number? Well, that means you check two paths and you got the same number. Does that prove that the limit exists? No, it does not. You got to check all paths, not just a pair of them. Let's do another example. Okay, show the limit doesn't exist. So let's do the thing we do. On the x equals 0 path. Now I'm picking these because we've done two examples and they worked. So coming in on the y-axis when x is equal to 0, so x is already equal to 0, I'm getting 1, y squared over y squared. So coming in on that, it's a constant. The function is just 1 on that whole graph. On y equal to 0, oh, I'll put it in, but I can already see there's going to be a problem here. Or at least I'm not going to be able to finish it as nicely as those other two examples. On y is equal to 0, all along that curve, this and this cancel out, so I also get 1. So this is inconclusive. I get 1 on coming in on this axis, I get 1 coming out on this axis, but that's not all paths. Let's try something else. And the thing I want to try is, what if I were to come in on a different line? So what I'm saying is here's our y, here's our x. We came in this way, we got 1. We came in this way, we got 1. What if we come in at some other line and see if we can get a different number? What is this line? Well, it has to go through the origin because we're approaching 0, 0. So I'm going to call this the line y equals mx. So I'm not saying what the m is yet. So I'm going to approach on the line y is equal to mx. So on that line, everywhere on that line, everywhere there's a y, I'm going to put mx. So I'm getting rid of all the y's. So then it's still going to be the limit as x approaches 0, because if I'm on that line, if x goes to 0, it forces y to equal 0. So now I've got my expression. If I'm on the line y equals mx, every y is going to be turned into mx. So this is going to be m squared x squared. M squared x squared. And this is going to be mx here. So now everything's in terms of x, and x is approaching 0. Now I can factor an x squared out the bottom and cancel it with the x squared out the top that I have. Let's put a comma in here. So I'm going to do that. I'm not taking the limit yet. If I factor an x squared out the top, if I factor an x squared out the bottom, now the x squareds can cancel, and if I take there's no more x's left, so I take the limit as x goes to 0. I'm getting, well, what am I getting? I'm getting an expression that's different for different m values. So if I would have taken on the line y equals 1x, I would have got 2 over 4. If I would have taken y equals 2x, I would have got 5 over 9. I get a different value. So since this depends on m, it's different for different paths, so the limit doesn't exist. So this sort of gives me all general lines. It also gives me, when m is equal to 0, that's this flat line here. So we already kind of checked that one. I guess this one is when x is equal to 0. That's like, we check this one when, no, we check this one when m is equal to 0, flat. This would be when m is equal to infinity. I don't want to think like that. Anyway, our answer is dependent on the slope of the line that we're come into, so that means the limit is different for different paths, therefore the limit doesn't exist. That's what we can say. Let's see what it looks like. So squared, squared, all squared. Oh, okay, I can see it here, right? As we approach, as you come in, it's only the 0, 0 point that's not defined, right? There's no break in it here. Well, let's look at our algebra. Our algebra says for our function that the only problem, the only dividing by 0 is going to happen on the y equals minus x line. So do I see that y equals minus x line? That's when we're shooting off to infinity. So that must be this line here. The program is connecting it here, but it really should be a line that goes all the way through. As you approach on different lines through, I'm getting different values going all the way to infinity, I guess. I can get from 0 to infinity, depending on what slope, depending on what m. Show that the limit doesn't exist. So this trick about, or this technique about approaching on all lines, you could do that first if you want, rather than check the two axes. Although mathematically, I think making x equal to 0 in my function and making y equal to 0 in my function, if it works, and it did in the first two examples, if it works, that's, I think mechanically that's the easiest thing to do. We just needed to resort to this other idea because it wasn't working. We got the 1 and the 1. Now, what if I would have approached on y equals mx and this would all canceled out? What if this would have equaled to 1? Now are we done and the limit exists? No, because that just means that all straight line paths are giving me 1. Maybe there's some kind of crazy spiral path that doesn't give me 1. So proving the limit does exist is quite a bit more difficult in multivariable calculus. It requires an epsilon delta proof. That's not in this video. So here's a function, and I'm telling you the limit exists. We could prove it with that epsilon delta if we knew how to do epsilon delta, which we don't. It's not in this video. But this limit does exist. So I get 0 from any path. Now, when we prove the limit exists, we're using the epsilon delta. It is analogous to the epsilon delta proofs that you might have done in your single variable calculus. Although maybe you skip that part. Lots of instructors skip the epsilon delta part. It is, I thought, one of the harder things to think about when I took single variable calculus back in the olden days. Anyway, the limit does exist. It's equal to 0. But take a look at this function. I can't just plug 0 in, 0, 0 in, because I get 0 over 0. So this limit exists, but this function is not continuous. What does it look like then? Well, let's take a picture. Let's see what, what function? We only see a limit there. I'm talking about this function. For this function, the limit as you approach the origin does exist. It is 0. But that's like that one point is removed. Now we're going to ask the machine to draw it. It might have trouble, but it won't be because of the math. It'll be because of the way the machine is drawing it. Let's check it out though. Let's give it a chance. So x squared y cubed and 2x squared plus y squared. No, okay. Actually, it didn't do too bad. There it is. It's continuous, it's smooth, it's continuous, it's differentiable everywhere. Although, I mean, the pictures are indicating that, it's not a proof, but every path I take into the origin is giving me 0, but it's not defined at the origin. So there's like a little hole in it. If I zoom in closer to, so it's not a continuous function, but the only problem is that one point. Let's zoom in a little closer just to see what's the what. Okay. It looks like, yeah, it's flat. When I approach it, it's still 0, but that point is missing. It's not continuous at that point. How can I make this continuous? Well, it's good everywhere except for 0, 0, 0. Right? If I could just fill that blue square in. So I'm going to do that by making this a split function. So f of x is equal to, I'm going to make it a split function. So it's equal to that if the xy point isn't the 0, 0 point. And it's equal to 0 if it is. So I made it a split function. All I'm doing is filling in that one little point. That would be, yeah, just put a dot there and that would smooth it over and make it a continuous function. So it's funny because normally we see piecewise functions and it makes it, it makes it not continuous or not differentiable. But here I've made it continuous now by filling in that point as a piecewise function.